Hello everyone. On our last lectures, we have studied about special function in which we had studied Hermite polynomial, Hermite polynomial, under which we have studied solution for solution of differential equation, differential equation for what? Hermite equation, or we can say this is a Hermite equation. We have studied the orthogonal property, orthogonal property, orthogonal property of Hermite polynomial, Hermite polynomial. Then we have studied the generating function, and then Roderick formula, Roderick formula, and few of recurrence recurrence relations. And regarding all these topics, we have studied numericals based on these numericals based on these topics. These topics. So with the same thing, we are going to study a new type of a special function. Name is Legendre polynomial. Legendre polynomial, or we can say that Legendre function. Legendre function. Same as the previous lecture, we should know the differential equation for Legendre polynomial. So the first is the differential equation. The differential equation for Legendre function. Legendre function is 1 minus x square d square y upon dx square minus of 2x dy upon dx plus n plus 1 y is equals to 0. Alright, where x is variable, n is some constant. Is known as, this differential equation is known as Legendre differential equation. It's known as Legendre differential equation. Say n is some integer, right? So if this is our differential equation for Legendre, so we need to know the solution for this differential equation. So as we have already done, just assume a solution. Say y is a solution for this differential equation. Says summation r tends to 0 to infinity, where some constant ar x to the power k minus 2r in a decreasing order. Alright. Be the solution for differential equation. So this is equation 2. Alright. So we know the differential equation for Legendre function. To know the exact solution for this differential equation, we have assumed a solution y, which is equals to summation r tends to 0 to infinity ar, where ar is some constant, is some coefficient. Alright, x to the power k minus 2r. So we know y is equals to summation r tends to 0 to infinity ar x to the power k minus 2r. Good. So from differential equation, we know we need to just differentiate this y with respect to x, which gives me summation r tends to 0 to infinity ar is some coefficient, and for the first differential equation, for the first differential order differentiation for this, y gives me k minus 2r x to the power k minus 2r minus 1. Good. From equation 1, I can see I need to differentiate y two times, right? So double differentiation of y with respect to x gives me summation r tends to 0 to infinity ar as it is k minus 2r, and if I differentiate this one more time, it will give me this power k minus 2r minus 1 here, x to the power k minus 2r minus 2. I know the value of y, I know the value of dy upon dx, and I know the value of d2y upon dx square. Substitute these three values, which equation 2, equation say 3, equation 4 in equation number 1. Our equation number 1 is 1 minus x square, which is a differential equation for Legendre polynomial, is d2y upon dx square minus 2x dy by dx, right, plus n plus 1, y is equals to 0. This was our first initial equation, so this is our differential equation. Alright, substitute this value in equation 1 in this term. This term we need to substitute what we have calculated earlier. Now just substitute this 1 minus x square. I know the value of d upon d2y upon dx square is summation r tends to 0 to infinity ar k minus 2r k minus 2r minus 1 x to the power k minus 2r minus 2. Alright, minus of 2x dy upon dx is summation r tends to 0 to infinity, this is ar k minus 2r x to the power k minus 2r minus 1. This is our dy upon dx. Just close this one too. Plus n plus 1, where n is our integer, and y is summation r tends to 0 to infinity ar k minus 2r, sorry, x to the power k minus 2r, which is equals to 0. We have substituted individually, but d2y upon dx square, dy upon dx, and y. Now just rearrange these equation in a decreasing term. Because why we had chosen decreasing term? Just because we have chosen our solution in decreasing order. So the maximum term will be, I will get, it will be power of x to the power of k minus 2 or y. Our first term is 2 minus 2 here, and if I multiply x square inside, so it will give me plus 2. This will cancel out. So the maximum term I can get, it will be x to the power minus k2 minus k to r. Good. So just rearrange this in terms of decreasing order. So due to this negative sign, first will give me Right, just remove this bracket too. Summation r tends to 0 to infinity. AR is constant. If I multiply x square inside, so this will give me this coefficient too. Which one? Just put it in bracket. This will give me k minus 2r, k minus 2r minus 1. Alright, and the power must be x to the power k minus 2r. If I see in this term, this will give me again what if I multiply x to this factor x to the power k minus 1. So this will again give me k minus 2r. So I know this term, this second term will give me x to the power k minus 2r term. So this is negative. I just taken out negative common. So this will give me a plus sign of 2 multiple factor of what? K minus 2r, right? And the last term, I can see the maximum power k, x to the power k minus 2r give me which n plus 1. So if this is of positive term, as I taken the negative sign common, so this will give me negative of n plus 1 multiply by x to the power k minus 2r. Good. So second highest term will be what? If I multiply this one inside, so this will give me x to the power k minus 2r minus 2. So plus, because this is plus, will give me only this term left when I multiply 1 with this term. So this will give me summation r tends to 0 to infinity ar, just put it in a large bracket, but k minus 2r, k minus 2r minus 1. What? Second highest term is x to the power k minus 2r minus 2, which is equals to 0. Alright, now just simplify this factor. Which one? This term. This term. Simplify this term. If I simplify this, just remove the negative sign here. So if I multiply minus 1 in a left hand side, so it will give me what? This term positive. So this will give me summation r tends to 0 to infinity ar. If I multiply this k minus 2r with this term, so this will give me k minus 2r to the power 2. And if I multiply k minus 2r with this minus 1 will give me what? Minus of k minus 2r. Alright, plus 2 minus k minus 2r minus of n plus 1. Alright, to the power x to the power k minus 2r negative of summation r tends to 0 to infinity. Just because we have taken we have removed this negative sign here, just we have multiplied minus 1 both the side, so this minus term becomes plus and this plus sign becomes negative of ar summation k minus 2r k minus 2r minus 1. Alright, where x to the power k minus 2r minus 2, which is equals to 0. I can see this both term can give me a single term. Which one? If I subtract this, so this will give me what? Okay, just simplify this term individually here. If I separate this here, which this term, alright, I'm using a different color for simplification. So I can write what? K minus 2r to the power 2 minus of k minus 2r plus 2 k minus 2r minus of n plus 1. Alright, so this will give me k minus 2r to the power 2 plus of k minus 2r minus of a multiply n square, and this will give me n if I took this one together. Alright, which k minus 2r to the power 2 minus n square plus k minus 2r minus n. I can write it this is a square b square, a square b square. I can add a square b square. I can use this formula. So according to this formula, it will give me what? A plus b, a minus b. Alright, so this will give me k minus 2r plus, if I use n, and this will give me k minus 2r plus n. Good. Plus, okay, if a plus b, just rearrange this, and plus n minus n. If I change the order, it will give me nothing change. Alright, plus this will k minus 2r minus n. As it is, I know k, this term is common in both, k minus 2r minus n. If I take it common, so the residue will be k minus 2r plus n plus 1. Alright, this. So in simplification, I can write it k minus 2r minus n, k minus 2r plus n plus 1. Alright, so this term can be written as this. So I just substitute. Our initial equation was summation r tends to 0 to infinity ar, instead of which this term, instead of say this term, I am rearranging what, k minus 2r minus n, k minus 2r plus n plus 1. Good. Where this becomes where x to the power k minus 2r minus of summation ar tends to 0 to infinity, where ar k minus 2r, k minus 2r minus 1, x to the power k minus 2r minus 2, which is equals to 0. Right. So this is the simplification of our equation. So if I take the coefficient of x to the power k, this is possible only when r is 0 in this term. If I put r is equals to 0 here, so this will give me k to the power x to the power k. Alright, so just put r equals to 0 here, so this will give me a 0, and due to r is 0, this term vanishes out, so k minus n, and k plus n plus 1 is equals to 0, because no other side, on the right hand side there is no any term of what, of k to the power x square, sorry, x to the power k. So we know the first term cannot be equals to 0, so k can take the value of n or n plus 1. Alright, either for justification of this equation, either a naught must be 0 or this term must be 0. So we know according to the first term cannot be over 0, so this can give me k minus n will give me what, if equals to 0, so this can give me k equals to n, or either k plus n plus 1 is equals to 0, so k will give me minus n plus 1. So I just simply written this here. Alright, so the k can take the value of n, and another value is minus n plus 1. If second lowest term I will calculate, coefficient of x to the power k minus 2. Just put it r equals to 1 here. So this will give me what, k to the power x to the power k minus 1, k minus 2, sorry. And here if I just put 2r equals to in this term, so for the first term I'll put what, r equals to 1, and for the second term I just need to put r equals to 2. All right. So here in this term, just put r equals to 1. So this will give me 1 a1 k minus 2 minus n. This will give me k minus 2. All right. If will give me 2, then this is going to be, okay, just write it as it 1 plus 1. And if here I put what, r equals to 2, this will give me 4 minus 2 6. All right. So I need to, for the second term, I need to just put here what, k minus 2. So just put it here, second term r equals to 0. Then only it will give me what, k minus, this will 0, so k minus 2. So just put in second term, which one, this second term, put r equals to 0, minus of a0. All right, minus of a0, the first term is k, and this will give me k minus 1, which is equals to 0. So a1 will become what, a1 in terms of a0, it's k minus 1 upon k minus 2 minus n, and this becomes k plus n minus 1, which is of a0. So I had calculated a1 in terms of a0. So coefficient for the general term, coefficient of what, x to the power k minus, say, 2r in general. If I need to calculate k minus 2r, so first term is as it is, and for here I need to put what, r equals to r minus 1. So all right, if I put here r equals to r minus 1, if I put r equals to r minus 1, so this will give me what, k 2 r minus 1 minus 2, so k minus 2r plus 2 minus 2 cancel out, so this will give me k minus 2r. So second term will give me k minus 2r when I put r equals to r minus 1 in this term. This is good, this is as it is, because this is already the coefficient of what, and this is coefficient for what, x to the power k minus 2r. So coefficient of k minus 2r will give me what, as it is, ar k minus 2r minus n, k minus 2r plus n minus 1, sorry, plus 1. This is plus 1, I think. Good, plus 1. Minus of, now I put what in second term? In second term, put r equals to r minus 1. R equals to r minus 1. So the r becomes r minus 1. And this becomes k minus 2r plus 2 and k minus 2r plus 2 minus 1 equals to 0. Good. All right. Need to calculate AR from this equation. So AR is, over here this becomes k minus 2r plus 1 from here, and this becomes k minus 2r plus 2. All right, whole upon multiple of what, AR minus 1. Here it goes k minus 2r minus n, k minus 2r plus n plus 1. Good. So I know the value of AR in terms of AR minus 1. I know the value of k can be n minus n plus 1. So for k equals to n, for k equals to n, ar must be your what? N minus 2r plus 1. Just substitute k, just substitute n in terms of in k. So the first term becomes your what? N minus 2r plus 1, n minus 2r plus 2 whole upon, if I substitute here n, so n and n will be added of negative of 2n. Sorry, our k is n positive, no? Alright, so n, this becomes 2r minus n, k minus 2r, sorry, this must be your n minus 2r plus n plus 1 multiple of ar minus 1, here cancel out. So final ar will be what? N minus 2r plus 1, n minus 2r plus 2 whole upon minus 2r, here becomes your what? 2n minus 2r plus 1 in terms of ar minus 1. So we had calculated what? Our ar in terms of ar minus 1. Just put r equals to 1. Put r equals to 1. So this will give me a1. Alright. So the first term will be what? N minus 2 plus 1, n minus 2 plus 2 whole upon minus 2, 2n minus 2 plus 1. This is a0. 1 minus 1 is 0. So a1 will become, this will cancel on, this becomes n minus 1. This will give me minus of 2 of 2n minus 1 into a0. So we had calculated a1 in terms of a0. If I need to calculate what? a2, just put r equals to 2. So this will give me 2 a2. So a2 will be what? a2 will be what? a2 will be what? Put r equals to 2. So the n minus 4 plus 1 here. This become n minus 4 plus 2 whole upon minus 2 multiple of 2. Here 2n minus 4 plus 1. Just this is a1. 2 minus 1 is 1. This will give me n minus 3. This will give me n minus 2 whole upon this will give me what? Minus of 4 and 2n minus 3. What? a1. I know a1 in terms of a0. Substitute a1 here. So n minus 3, n minus 2 whole upon minus 4 of 2n minus 3. Just put a1. a1 is your n minus 1 whole upon minus 2, 2n minus 1 multiple of a naught in terms of a1. Just your final a2 becomes your what? N minus 3, n minus 2, n minus 1 into n whole upon minus minus plus 2 multiple 4, 2n minus 1, 2n minus 3, a naught. Alright. So we can say therefore the solution of Legendre differential equation differential equation. Differential equation for what? K equals to n. For k equals to n, give me what we had calculated. We had assumed r in y equals to 0 to a naught. A naught. Sorry, this is ar. For generalized term, this is ar x to the power k minus 2r. All right. We said just expand this in terms of sequential form. So this will give me a0 k to the power a0 a0 x to the power k for r equals to 0. Then after r equals to 1, this will give me a1 x to the power k minus 2. Again, this is a2. This will be x to the power minus 4. And the series goes on. Just we had calculated the coefficient in terms of a naught already. So if I take it out, what a naught common. So for k equals to n, either we can change it. This can be changed as n. Here n minus 2 and here n minus 4 x to the power p. Alright, so this will give me x to the power n minus of first a1 term. A1 term is here. How much this? N minus 1 this term. So this is of negative signs first. Give me negative of n minus 1 upon 2 2n minus 1 x to the power n minus 2. This is from here plus third term is n minus 1 n minus 2 n minus 3 upon this term, this value a2 in terms of this 2 multiplied by 4 n 2n minus 1 2n minus 3 x to the power n minus 4 plus so this will be a negative term and so on. If we put a naught is how much 1.3.5 up to what 2n minus 1 upon factorial n. So our y will be Legendre polynomial. Our yx will be treated as Legendre polynomial, where Pn is Legendre symbol for Legendre polynomial. Legendre polynomial. Alright. Only when if I put the value of a naught is equals to 1.3 as to so on what 2n minus 1 upon factorial n, then yx will be pnx. So yx is our now pnx Legendre polynomial, which is equals to y, which is equals to a naught is here a0 is 1.3 dot multiply up to what 2n minus 1 upon factorial n. First term is xn minus n minus 1 upon 2n minus 1 x to the power n minus 2 plus n minus 1 n minus 2 n minus 3 as it is. I'm just rewriting it this here 2.4 multiple of 2n minus 1 2n minus 3 x to the power n minus 4 minus up to so on. So this is our Legendre polynomial solution. All right. So second solution, we can also calculate second solution. Simple word. Second solution will be second solution for what? For k equals to minus n plus 1. Just substitute here what k equals to n plus 1. So the second term, the second solution, one solution is this. Second solution is denoted by q and x. All right, where n is on subscript. All right, where n is in a subscript, and then the complete, you can say, then the complete solution will be complete solution of what? Legendre differential equation. Equation will be what? Y equals to c1, some coefficient pnx plus c2 qnx. So this is the complete solution. One of solution we have calculated. You can calculate same as what second calculation for this Legendre differential equation. So for the final legend, the complete solution of y will be c1 p1x plus c2 q1x. So this is it for now. In next lecture, we will see the generative function for Legendre polynomial. Thank you.